Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle into whatever surface is supporting you right now. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the day is finally releasing its hold on you? Tonight we're going to explore something that exists only in imagination, but is grounded entirely in reality. We're going to ask a simple question. What if you could fly through every galaxy in the observable universe? What would you see? What would you discover? What would change inside you as you witness 200 billion galaxies, each containing hundreds of billions of stars, each star perhaps circled by worlds we'll never name? It's a journey that spans 93 billion light years and takes us to the very edge of everything we can see. But don't worry. This isn't going to be a frantic race through space, a breathless catalogue of cosmic objects. Instead, we'll move slowly and carefully through this impossible voyage, taking our time with each discovery, pausing to contemplate what each galaxy might teach us. By the end, I think you'll find that this journey is less about the destination and more about what happens to our perspective when we truly comprehend the scale of existence. If you enjoy these calm explorations of cosmic possibilities, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here. Your presence means more than you know. So settle in, let your shoulders drop, take a slow breath, and let's begin our slow drift through every galaxy in the universe. There's nowhere you need to be right now, nothing you need to do but listen. We have all the time in the world and beyond. Let's begin. Before we launch ourselves into this impossible journey, let's consider what it would mean to fly through every galaxy. Not the logistics of such a voyage, which defy every law of physics we know, but rather what we'd need to understand before we began. Imagine, if you will, a vessel unlike any craft humans have ever conceived. It would need to move faster than light itself, far faster, skipping across cosmic distances that normally require millions or billions of years to traverse. Let's say, for the sake of our journey, that we could move at whatever speed the moment required. Sometimes we'd crawl, taking hours to drift through a single galaxy, savouring its spiral arms and glowing nebulae. Other times we'd leap across voids so vast that entire galaxy clusters would blur past like cities seen from an airplane window. The observable universe, as we understand it in the early 21st century, contains somewhere between 200 billion and 2 trillion galaxies. That number shifts depending on how we count, how sensitive our instruments become, how we define a galaxy versus a dwarf galaxy or a satellite system. For our journey, let's settle on 200 billion as our destination count. 200 billion separate island universes, each a complete cosmos unto itself. And this brings us to something we should contemplate before we leave. Each of those galaxies is unreachable to humanity in any practical sense. The Andromeda Galaxy, our nearest large galactic neighbour, is 2.5 million light-years away. Even if we could build a spacecraft that travelled at nearly the speed of light, the journey would take 2.5 million years. The astronauts who left would arrive in a future so distant that humanity itself might no longer exist. And Andromeda is close, almost absurdly close on cosmic scales. But there's something beautiful about this impossibility, because we're not bound by spacecraft or lifespans or the speed of light tonight. We're going to do what humans do best when confronted with limits. We're going to imagine. We're going to take a journey that could never happen, and in doing so, we're going to understand something true about the universe we actually inhabit. So let's begin. Picture yourself at the starting point. Not Earth, precisely, but somewhere just outside our galaxy, the Milky Way. You're hovering in the space between stars, looking back at the galaxy that contains everything humanity has ever known. Are you ready? Take a breath. Let's drift toward that first light. From outside, the Milky Way is heartbreakingly beautiful. You've seen images, of course, artistic renderings based on observations and mathematical models, because we've never actually photographed our galaxy from outside. We're embedded in it, trapped in its disk, looking edge-on at our own cosmic home. But if we could float here, perhaps 100,000 light-years from the galactic centre, we'd see what we've only imagined, a spiral. Vast and turning, though moving so slowly that you'd need to watch for millions of years to see the rotation. 4 major arms of stars and gas and dust, curving outward from a bright central bulge. The whole structure perhaps 100,000 light-years across, though its edges are fuzzy, debatable, fading gradually into the dark. 200 to 400 billion stars wheeling together in a cosmic dance that's been continuing for more than 13 billion years. You can see where we are, or were, about 2/3 of the way out from the centre, in a minor spiral arm called the Orion Spur. From here, the sun is invisible, just one yellow star among hundreds of billions. Earth is less than invisible. It's a mathematical improbability, a speck of rock so small that even if you knew exactly where to look, you wouldn't see it. And yet, on that speck, every human who has ever lived was born, lived, and died. Every war, every love story, every discovery, every triumph and tragedy, all of it on that invisible speck. Let's drift closer for a moment. As we approach the outer edges of the galaxy, we begin to pass through the galactic halo, a region of space populated by ancient globular clusters. These are tight spheres of stars, hundreds of thousands of them packed into a volume just a few dozen light-years across. The stars here are old, some of the oldest in the galaxy, formed when the universe was young and composed mostly of hydrogen and helium. They glow with a reddish light. The colour of age. Moving inward, we enter the disk. This is where most of the galaxy's stars live, where most of its star formation happens. Here, in enormous nebulae, new stars are being born even as we pass. The Orion Nebula, visible from Earth as a fuzzy patch in the constellation Orion's Sword, is a stellar nursery where thousands of stars are igniting for the first time. We could spend years here, watching protostars coalesce from clouds of gas, witnessing the moment when fusion begins in their cores. But we have 200 billion galaxies to visit, so we take one last look at home, at the spiral arms glowing with the light of young blue stars, at the dark lanes of dust where future stars are gestating, at the bright core where a supermassive black hole with the mass of 4 million suns holds court. We commit it to memory, and then we turn away. The journey to the next galaxy begins now, and with it, we start to understand what cosmic distance truly means. The space between the Milky Way and Andromeda is called the local void, though that name is a bit misleading. It's not completely empty. There are dwarf galaxies here, small irregular collections of stars gravitationally bound to either the Milky Way or Andromeda. There's gas, though incredibly diffuse, perhaps 1 atom per cubic metre. There's dark matter, that mysterious substance that makes up most of the mass in the universe but doesn't interact with light. We can't see it, but we can feel its gravitational influence, the way it bends space and guides the motion of galaxies. As we cross this void, accelerating to speeds that make light seem slow, we might wonder what it would feel like to be here, truly here, halfway between galaxies. The Milky Way behind us would appear as a distant smudge of light. Andromeda ahead would look similar, though slightly larger. Every other galaxy would be invisible to the naked eye, too far away to register without a telescope. The sky wouldn't be black so much as an absence of anything. No stars, no galaxies, just darkness. Human beings evolved under a sky full of stars. Even the darkest night sky on Earth is busy with light, thousands of visible stars, the glow of the Milky Way arcing overhead. But here, in the intergalactic void, there would be nothing. An astronaut drifting here would see perhaps a dozen fuzzy patches of light, the nearest galaxies, and nothing else. It would be the loneliest place imaginable. But let's think about time for a moment. We're moving impossibly fast, but even at the speed of light, this journey would take 2.5 million years. During that time on Earth, the entire course of human evolution would have played out. The first members of the genus Homo appeared roughly 2.5 million years ago. If we'd started this journey then, at the speed of light, we'd only now be arriving at Andromeda, and this is just the first step. We have 200 billion galaxies to visit. If we spent even one day in each galaxy, the journey would take 547 million years. Complex life on Earth has only existed for about 540 million years. We could span the entire history of animals, from the Cambrian explosion to today, and still not finish our tour. So we adjust our thinking, we move faster, we compress time differently. This is imagination after all, not physics. We decide that we'll spend as long as we need in each galaxy to understand it, and then we'll move on. Time becomes elastic, subordinate to experience rather than the other way around. Andromeda grows larger ahead of us. We're nearly there. Let's cross these final light years together and see what awaits. Andromeda fills the sky ahead of us now, and it's magnificent in a way that's difficult to put into words. It's larger than the Milky Way, perhaps half again as massive, containing roughly 1 trillion stars to our few hundred billion. Its spiral arms are tighter, more defined, glowing with the light of millions of young blue stars. At its heart, like ours, a supermassive black hole, though this one is far larger, perhaps 50 million times the mass of the Sun. As we approach, we can see that Andromeda is not alone. It has satellite galaxies, smaller companions that orbit it like moons around a planet. M32 and M110 are visible, compact elliptical galaxies that have been gravitationally stripped of much of their star-forming gas by Andromeda's immense gravity. There are others too, dwarf spheroidal galaxies too faint to see without instruments, each containing just a few million stars. Let's enter Andromeda's disk and drift through its spiral arms. Here, we see star formation on a scale that dwarfs what happens in the Milky Way. Enormous nebulae, hundreds of light years across, glow with the energy of newborn stars. These are regions where the gas is so dense that gravity pulls it together into star clusters, containing tens of thousands of suns, all born from the same natal cloud, all roughly the same age. We pass through a region of dark dust lanes, where the light of background stars is blocked by clouds of particles so fine they're measured in microns. This dust is the debris of previous generations of stars, the raw material from which new stars will form. It contains carbon and silicon, oxygen and iron, all the heavy elements forged in the cores of stars that lived and died billions of years ago. Near the galactic core, things become more crowded. Stars here are packed more densely than in the outer regions, sometimes separated by just a fraction of a light year. If Earth existed here, the night sky would be ablaze with stars so bright they'd cast shadows. There would be no darkness, just varying degrees of starlight, and at the very centre we find the black hole. We can't see it directly, of course. Black holes by definition emit no light. But we can see its effects. Stars orbit it at incredible speeds, some completing an orbit in just a few hundred years despite being light years away from the event horizon. Gas falls toward it in a spinning accretion disk, heating to millions of degrees and emitting X-rays before vanishing beyond the point of no return. We could spend a lifetime here and never see everything Andromeda has to offer. But we've made a commitment. 200 billion galaxies await. So we climb out of Andromeda's gravity well, accelerate back to our impossible speed, and look ahead to the local group, the cluster of galaxies that includes both the Milky Way and Andromeda, along with more than 50 smaller companions. Our next stop is already in view. The Triangulum Galaxy, M33, smaller than both the Milky Way and Andromeda, but beautiful in its own quiet way. Let's go see what it holds. The Triangulum Galaxy is sometimes called the pinwheel because of the way its spiral arms seem to radiate from its core in an almost perfect geometric pattern. It's about 60,000 light-years across, smaller than the Milky Way, and contains perhaps 40 billion stars. By cosmic standards, it's a medium-sized galaxy, neither giant nor dwarf, just somewhere comfortably in between. What's immediately striking as we approach is how face-on it appears. Unlike the Milky Way, which we'd see edge on from most angles outside it, or Andromeda, which is tilted at an angle, Triangulum presents its full spiral structure to our view. We can see every arm, every bright knot of star formation, every dark lane of dust. It's like looking at a cosmic mandala, a pattern so perfect it almost seems designed. We drift through Triangulum's outer regions where star formation is less active, where older red and yellow stars dominate. Then we move inward, toward the bright nebulae where new stars are being born. One region in particular catches our attention, NGC 604, one of the largest star-forming regions known in the local group. It's nearly 1,500 light-years across, 40 times the size of the famous Orion Nebula, and contains more than 200 of the hottest. Most massive stars we've ever observed all clustered together in one place. The radiation from these massive stars has carved a bubble in the surrounding gas, creating a cavity where only the most intense stellar winds exist. In a few million years, these stars will explode as supernova, possibly triggering new waves of star formation in the compressed gas around them. The cycle continues, generation after generation, as long as the galaxy has gas to fuel it. But let's pause here and consider the dwarf galaxies that populate the local group. There are more than 50 of them, small irregular collections of stars that orbit either the Milky Way or Andromeda. The large and small Magellanic Clouds, visible from the southern hemisphere of Earth, are two examples. Each contains just a few billion stars, a fraction of what a full-size galaxy holds, but they're galaxies nonetheless, complete stellar systems with their own histories. As we visit these smaller worlds, we start to notice something. Many of them are being torn apart by the gravity of their larger neighbours. The Sagittarius dwarf galaxy, for instance, is currently passing through the Milky Way's disk. With each passage, more of its stars are stripped away and absorbed into the Milky Way's halo. In another billion years, it will cease to exist as a separate entity. It will have been cannibalized, consumed by a larger predator. This is how galaxies grow. They merge and collide, absorbing smaller systems, occasionally colliding with galaxies of comparable size in cosmic catastrophes that reshape both participants. The Milky Way and Andromeda themselves are on a collision course, destined to merge in about 4.5 billion years into a single giant elliptical galaxy that astronomers have already nicknamed Milkomeda. But that collision is still in the future. For now, these galaxies exist separately, each a distinct world. And we've only seen 3 of the 200 billion that await us. It's time to leave the local group behind and venture into the greater universe beyond. The Virgo cluster lies ahead, containing more than 1,000 galaxies. Let's accelerate toward it and see what cosmic city awaits. The journey to the Virgo cluster takes us across 50 million light-years, a distance so vast that we leave behind everything we might consider our cosmic neighbourhood. The local group with its dozens of galaxies fades behind us. Ahead, something much larger takes shape. Galaxy clusters are among the largest gravitationally bound structures in the universe. They're collections of hundreds or thousands of galaxies, all held together by mutual gravity, all orbiting a common centre of mass. The Virgo cluster is one of the nearest to us, and it contains somewhere between 1,000 and 2,000 galaxies, depending on how we define its boundaries. As we approach, the first thing we notice is M87, the supergiant elliptical galaxy at the cluster's heart. It's enormous, one of the most massive galaxies in our cosmic region, containing perhaps several trillion stars. While spiral galaxies like the Milky Way are still actively forming stars, elliptical galaxies like M87 are mostly finished with that process. Their stars are old, and they glow with a reddish-yellow light that speaks of age and stability. At the centre of M87 lies one of the largest black holes ever discovered. In 2019, scientists released the first actual photograph of a black hole's event horizon, and this was the black hole they chose. It has a mass of 6.5 billion suns, and its event horizon, the point beyond which nothing can escape, is larger than our entire solar system. Looking at it, even from a safe distance, we feel the weight of its presence, the way it warps space around itself, bending the paths of light and matter. But M87 is just one galaxy among many. As we drift through the Virgo cluster, we pass spiral galaxies and ellipticals, lenticular galaxies that are somewhere between the two, and irregular galaxies that defy easy classification. We see galaxies in the process of colliding, their spiral arms warped and stretched by tidal forces. We see galaxies that have been stripped of their gas by the hot plasma that fills the space between cluster members, leaving them unable to form new stars. The cluster itself is embedded in a massive cloud of hot gas, heated to millions of degrees by the gravitational energy of the cluster. This gas outweighs all the visible stars in all the galaxies combined. It's invisible to optical telescopes but glows brightly in X-rays. If we could see in that wavelength, the entire cluster would appear to be filled with a luminous fog, brightest at the centre, where M87 holds court. And here's something worth contemplating. Galaxy clusters like Virgo are held together by dark matter. The visible matter, all the stars and gas we can see, isn't massive enough to generate the gravity needed to bind the cluster. There must be something else, something that doesn't emit or absorb light, something we can only detect through its gravitational effects. It outnumbers visible matter by a factor of 5 to 1, maybe more. The universe is made mostly of things we can't see. We could explore Virgo for years and never see all it has to offer. But there are other clusters ahead, larger and farther away. The Coma cluster contains more than 1,000 galaxies and lies 300 million light-years distant. Beyond that, the universe organises itself into even larger structures, filaments and sheets of galaxy clusters separated by vast voids. Our journey is starting to reveal not just individual galaxies, but the cosmic web itself, the underlying structure of everything. Let's continue onward. The Coma cluster awaits, and beyond it, structures so large they challenge our ability to comprehend scale. As we travel deeper into space, farther from home, a pattern begins to emerge. Galaxies aren't distributed randomly across the universe. They cluster together in groups and clusters, and those clusters align into larger structures called superclusters. And those superclusters form filaments, long chains of galaxy clusters that stretch across hundreds of millions of light years. Between these filaments lie voids, regions of space that contain very few galaxies. These voids are enormous, sometimes 300 million light-years across. If you were located in the centre of a void, the nearest galaxy might be 100 million light-years away. The sky would be nearly empty, with just a handful of distant smudges visible even with the most powerful telescopes. Let's pause our journey for a moment and pull back, as if we're looking at a map of the universe on the largest possible scale. What we see resembles a foam, or a sponge. The filaments are like the solid parts of the sponge, and the voids are like the empty spaces between. This structure, this cosmic web, formed in the early universe as dark matter clumped together under its own gravity, and normal matter followed, pulled into the gravitational wells created by the dark matter. The largest of these structures have names. The Sloan Great Wall is a filament of galaxies that stretches for over 1 billion light-years. The Hercules Corona Borealis Great Wall might be even larger, though its existence is debated. These structures are so vast that light takes hundreds of millions of years to cross them. They're the largest known structures in the universe, and they represent the limit of how large things can get while still being gravitationally bound together. As we fly through one of these filaments, passing galaxy cluster after galaxy cluster, we start to notice differences between galaxies in clusters and galaxies in the voids. Cluster galaxies tend to be older, redder, more elliptical. They've been through more mergers and collisions. They've had their star-forming gas stripped away by interactions with other galaxies and with the hot intracluster medium. They're settled, mature, past their prime. Void galaxies, by contrast, tend to be younger, bluer, more actively forming stars. They're isolated, free from the violent interactions that reshape cluster galaxies. They evolve at their own pace, peacefully converting gas into stars over billions of years. And this teaches us something important. Environment matters in the universe, just as it does on Earth. Where a galaxy lives determines how it evolves, what it becomes. A spiral galaxy born in a rich cluster might be transformed into an elliptical through mergers, or stripped of its gas and left as a red and dead lenticular. The same galaxy born in a void might remain a spiral forever, never encountering another large galaxy in its entire lifetime. We're beginning to understand that galaxies aren't isolated objects. They're part of a larger ecosystem, a cosmic web of matter and energy that shapes their evolution just as surely as genetics and environment shape the evolution of the living things on Earth. Each galaxy is both an individual and part of a vast community, connected to everything around it through gravity's invisible threads. As we continue our journey, flying through filament after filament, pausing to explore the galaxies we find most interesting, we carry this understanding with us. We're not just seeing galaxies, we're seeing a universe that organizes itself, that has structure and pattern on every scale from planets to superclusters. It's a thought worth holding as we press onward into ever more distant reaches of space. Not all galaxies fit neatly into the categories we've discussed. As we venture farther from home, we encounter stranger forms, galaxies shaped by catastrophic events into configurations that defy our expectations. Consider the Cartwheel Galaxy, located roughly 500 million light-years from Earth. It's a ring galaxy, and it looks exactly like its name suggests, a bright ring of stars and gas surrounding a fainter central region, with spokes of material connecting the ring to the core. What could create such a structure? The answer is violence. Some 100 million years ago, a smaller galaxy plunged straight through the Cartwheel's disk. The collision didn't destroy either galaxy, but it sent a ripple of density through the Cartwheel like a stone thrown into a pond. That ripple compressed the gas as it expanded outward, triggering a wave of star formation that created the ring we see today. The smaller galaxy, having passed through, continues on its journey, now millions of light-years away. We see other collision-shaped galaxies as we travel. The Antennae galaxies, two spiral galaxies in the process of merging, have been stretched by tidal forces into long tendrils that extend for hundreds of thousands of light-years. Where the two galaxies overlap, star formation is proceeding at a furious rate. In another few 100 million years, they'll complete their merger and form a single elliptical galaxy, all trace of their spiral structure erased. There are galaxies called Hoag's object, perfect rings with almost nothing in the centre, galaxies whose origin is still debated. There are polar ring galaxies, where a ring of stars and gas orbits perpendicular to the main galactic disk. There are jellyfish galaxies, spirals that are falling into galaxy clusters and being stripped of their gas, leaving long tentacles of star formation trailing behind them like the tentacles of a jellyfish. Each strange galaxy tells a story. Most galaxies we see appear normal because we're catching them at a quiet moment in their evolution. But every galaxy goes through periods of upheaval, of mergers and collisions, of gas stripping and tidal distortion. We're just fortunate enough on our impossible journey to see galaxies caught in the act of transformation, and this brings us to something worth contemplating. In a few billion years, the Milky Way and Andromeda will collide. For 1 billion years or more, they'll orbit each other, stretching and warping under mutual gravitational stress. The spiral arms will be disrupted. Streams of stars will be flung into intergalactic space. New bursts of star formation will ignite as gas clouds collide and compress. From Earth, If humanity still exists and if Earth is still habitable, the night sky will be spectacular. Andromeda will grow larger year by year, eventually filling half the sky. New stars will blaze to life in the regions where the two galaxies overlap. Eventually, the galaxies will settle into a single elliptical system, larger than either progenitor, and the cosmic dance will end. But here's the remarkable thing. Despite the violence of such collisions on galactic scales, individual stars almost never collide. Space is so vast and stars are so small that two galaxies can pass completely through each other without a single stellar collision occurring. The Sun and Earth would likely survive the merger unscathed, perhaps flung into a different part of the new galaxy, perhaps seeing a different set of stars in the night sky. But fundamentally unchanged. Galaxies collide. Stars pass by each other like ghosts. It's another reminder of the scale we're dealing with, the vast emptiness that makes up most of the universe. As we continue our journey, passing through more and more galaxies, this becomes clearer. We're flying through spaces so large that even stars, those massive balls of plasma, are like dust motes floating in a cathedral. Let's move onward. There are quasars ahead, the brilliant cores of active galaxies powered by supermassive black holes consuming matter at prodigious rates. They're some of the brightest objects in the universe, and they're calling to us across billions of light years of space. As we journey farther from Earth, moving deeper into space, we're also travelling backward in time. Light takes time to cross cosmic distances, so when we look at a galaxy a billion light years away, we're seeing it as it was a billion years ago. The farther we travel, the younger the galaxies we encounter become, and at a certain distance, roughly 10 to 12 billion light years from Earth, we enter the Quasar Era. A time when the universe was much more violent than it is today. Quasars are the luminous cores of galaxies powered by supermassive black holes that are actively feeding. Matter falls into these black holes in enormous accretion disks, spiraling inward, heating to millions of degrees, emitting radiation across the entire electromagnetic spectrum. A single quasar can outshine its entire host galaxy, emitting as much light as 1 trillion stars from a region smaller than our solar system. As we approach our first quasar, we're struck by its brilliance. Even from millions of light years away, it blazes in the darkness like a searchlight. As we draw closer, we can see jets of material being ejected from near the black hole's poles, travelling at nearly the speed of light, extending for hundreds of thousands of light years into space. These jets are powered by the rotational energy of the black hole itself, and they pump enormous amounts of energy into the surrounding intergalactic medium. The host galaxy is harder to see, overwhelmed by the light of the quasar at its heart, but as we orbit, shielding our eyes from the central glare, we can make out its structure. It's a spiral, but heavily disrupted, possibly in the process of merging with another galaxy. The merger has funneled gas toward the central black hole, providing the fuel for the quasar's brilliance. What we're witnessing is a phase that most galaxies go through at some point in their evolution. When two galaxies merge, their central black holes eventually settle toward the centre of the new combined galaxy. On the way, they consume enormous amounts of gas and dust, briefly shining as quasars before exhausting the nearby fuel supply and going quiet. The Milky Way's central black hole is quiet now, but it may have been a quasar in the distant past, and it might be again when Andromeda arrives and the merger begins. As we explore this epoch, travelling from quasar to quasar, we notice that star formation rates were much higher in the early universe. Galaxies were smaller and contained more gas, and they collided more frequently in the denser early universe. The result was an era of intense activity, of rapid star formation and quasar activity that has gradually declined over cosmic time. By the present day, in the local universe, most galaxies are quiet. Their central black holes are dormant. Star formation continues, but at a much reduced rate compared to 10 billion years ago. The universe is settling down, maturing, moving from a wild youth to a quieter middle age. But we're not in the present day anymore. We're in the past, and the farther we go, the younger the universe becomes. At some point, if we travel far enough, we'll reach a time before galaxies existed at all, when the universe was just a hot soup of hydrogen and helium cooling after the Big Bang. But that's still ahead of us. For now, we're in an era of cosmic brilliance, of quasars and starbursts, of galaxies colliding and black holes feeding. It's spectacular, almost overwhelming in its energy. And yet there's something wistful about it too, because we know that this era is temporary. These quasars will exhaust their fuel, these galaxies will complete their mergers, the universe will quiet down. What we're seeing is a moment of peak activity, never to be repeated. Let's linger here for a while, soaking in the light of a billion quasars, before we push even farther back in time to see what galaxies looked like when the universe was truly young. We're travelling backward through time now, crossing billions of years with each leap forward through space. The galaxies around us are becoming smaller, less structured, more chaotic. We're approaching the cosmic dawn, the era when the first galaxies formed. The James Webb Space Telescope, launched in 2021, has given us our first clear views of this epoch. What it's shown us is both expected and surprising. The first galaxies were indeed smaller than modern galaxies, often just a few billion stars rather than hundreds of billions. But they were also forming stars at astonishing rates, converting their gas into stars far faster than galaxies do today. As we arrive in this early epoch, roughly 12 to 13 billion years ago, we can see these first galaxies taking shape. They're irregular, messy, lacking the well-defined spiral arms or elliptical shapes we see in modern galaxies. They're being fed by streams of fresh hydrogen falling in from the intergalactic medium, and they're colliding and merging with each other constantly in the dense early universe. The stars in these galaxies are different too. The very first stars, formed before any galaxies existed, contained almost no elements heavier than hydrogen and helium. Carbon, oxygen, nitrogen, iron, all the elements that make up planets and people, didn't exist yet. They had to be created in the cores of stars and scattered into space when those stars exploded. By the time we're seeing in this epoch, several generations of stars have already lived and died. Heavy elements exist, but they're still rare. If we could examine a planet in one of these early galaxies, we'd find it made of simpler materials than Earth. Life, if it exists at all, would have to work with a limited palette of elements. But what strikes us most as we explore these early galaxies is their sheer abundance. There are so many of them, so densely packed, that collisions and mergers are happening constantly. The process of hierarchical structure formation, the gradual build-up of small galaxies into larger ones, is in full swing. Every galaxy we see will eventually merge with others to form the larger galaxies we know from the present day. And beyond these galaxies, if we could look farther still, we'd see the cosmic dark ages, the period before the first stars formed when the universe was filled with neutral hydrogen, opaque to most wavelengths of light. But we can't see into that era directly because there are no stars to provide light. We can only infer what it was like from computer simulations and from the cosmic microwave background, the afterglow of the Big Bang itself. We've come so far, seen so many galaxies, and we've barely begun our journey. We've visited perhaps a few hundred galaxies out of the 200 billion that exist, and already we're starting to feel something change inside us, a shift in perspective, a growing understanding of what it means to be a tiny consciousness embedded in something so vast. But let's not rush to conclusions. We have many more galaxies to see, many more wonders to encounter. The universe is far from done surprising us. Let's move forward through time again, returning to more recent epochs, and explore the diversity of galaxies that evolution has produced. Having seen the early universe, let's return to more recent cosmic times and explore the different types of galaxies in more detail. We've discussed elliptical galaxies in passing, but they deserve our closer attention because they represent the end state of galactic evolution, the final form that many galaxies achieve after billions of years of mergers and growth. elliptical galaxies come in a range of sizes. Some dwarf ellipticals contain just a few million stars and are smaller than a single spiral arm of the Milky Way. Others, called giant ellipticals or CD galaxies, sit at the centres of galaxy clusters and contain trillions of stars, having grown fat on the consumption of smaller galaxies over billions of years. As we approach a giant elliptical, M87 perhaps, or one of the other supergiant ellipticals that populate the centres of rich galaxy clusters, we notice immediately how different it is from spiral galaxies. There are no spiral arms, no disk of stars rotating in a plane. Instead, stars orbit the galactic centre in random orientations, creating a three-dimensional distribution that's roughly spherical or ellipsoidal, hence the name. The stars here are old. When we analyse their light, we find that most of them formed more than 10 billion years ago. There's very little gas left in the galaxy, having been either consumed in past episodes of star formation or heated and expelled by supernova explosions and stellar winds. Without gas, no new stars can form, so the galaxy is slowly fading, its massive blue stars having long since exhausted their fuel and exploded, leaving only the longer-lived red and yellow stars to carry on. But don't mistake age for inactivity. These galaxies are dynamic in their own way. Stars move through the galaxy at hundreds of kilometers per second, though the galaxy is so large that it would still take a star millions of years to cross from one side to the other. Occasionally, two stars pass close enough to exchange orbital energy, one speeding up and one slowing down in a gravitational interaction. At the centre of the galaxy, the supermassive black hole sits dormant, having consumed most of the gas within reach. But even in its quietude, it shapes the galaxy around it. The gravitational influence of the black hole affects the orbits of stars for thousands of light years in every direction. Some stars orbit so close to the black hole that they complete an orbit in just a few years, whipping around at a significant fraction of the speed of light before being flung back out into the broader galaxy. Giant elliptical galaxies are also interesting because of what they contain beyond stars. Many of them have extensive systems of globular clusters, tight spheres of stars that orbit the galaxy like satellites. M87, for instance, has more than 12,000 globular clusters, each containing hundreds of thousands of ancient stars. These clusters formed when the galaxy was young. And they've remained intact ever since, surviving billions of years through the sheer strength of their internal gravity. And then there are the stellar populations we find scattered throughout these galaxies. When we analyse the light from different regions, we find evidence of past mergers. Some stars orbit in one direction, some in another, indicating that they came from different progenitor galaxies that merged to form the current giant. It's like archaeology, reading the fossil record of galactic history in the present-day distribution of stars. As we prepare to leave this elliptical giant, drifting back out into intergalactic space, we reflect on what these galaxies represent. They're the final chapter of galactic evolution, or at least a very late chapter. Most of their drama is in the past. They've already consumed their neighbours, already converted most of their gas into stars, already settled into a state of gradual decline. They'll continue to exist for trillions of years, their stars slowly burning out one by one, until eventually they're filled only with white dwarfs and neutron stars and black holes, the fading embers of stellar fires that burned bright billions of years ago. But there's a quiet dignity to them, a sense of completion. They've finished their journey. They're what the Milky Way and Andromeda will become eventually. And in that sense, visiting them is like looking at our own far future, seeing what will be when the story of our galaxy is mostly written. Not all galaxies age gracefully into elliptical retirement. Some remain chaotic throughout their lives, never settling into the ordered rotation of a spiral or the sedate randomness of an elliptical. These are the irregular galaxies, and they're among the most interesting objects we'll encounter on our journey. The Large Magellanic Cloud, visible from Earth's southern hemisphere, is a perfect example. It's a satellite of the Milky Way, orbiting our galaxy about once every billion years. It contains perhaps 30 billion stars, not enough to form the gravitational well needed to pull itself into a spiral, so it remains irregular, a messy collection of stars and gas with no clear structure. As we explore the Large Magellanic Cloud, we find regions of intense star formation. The Tarantula Nebula, one of the largest star-forming regions known, spans nearly 1,000 light-years and contains some of the most massive stars ever discovered. These stars burn so hot and bright that they're tearing the nebula apart with their radiation, creating a bubble of ionized gas that glows in stunning shades of red and blue. What's happening here is what astronomers call a starburst, a period of extraordinarily rapid star formation that converts gas into stars far faster than the steady background rate. Starbursts can be triggered by several mechanisms. Sometimes it's a collision with another galaxy, as the collision compresses gas clouds and triggers gravitational collapse. Sometimes it's a close gravitational encounter that doesn't result in a full merger, but still disturbs the gas distribution. Sometimes it's simply a concentration of gas that reaches a critical density and begins forming stars on its own. Whatever the cause, the result is spectacular. Starbursts can increase the star formation rate of a galaxy by a factor of 10, 100, even 1,000. They're brief on cosmic timescales, typically lasting just a few tens of millions of years before the available gas is exhausted or blown away by stellar winds and supernova explosions. But while they last, they're among the brightest phenomena in the universe. As we fly through the heart of a starburst galaxy, we're surrounded by brilliant blue stars, each dozens of times more massive than the Sun. They burn through their fuel at prodigious rates, living fast and dying young. The most massive ones will last only a few million years before exploding as supernova, scattering the heavy elements they've created throughout the galaxy. The interstellar medium here is a violent place. Stellar winds from massive stars slam into each other at speeds of thousands of kilometers per second, creating shock waves that heat the gas to millions of degrees. Supernova explosions send shells of expanding debris through the galaxy, triggering new waves of star formation when they compress fresh gas clouds. It's chaotic, energetic, almost overwhelming in its intensity. And yet there's something deeply creative about it. This is where new stars are born, where planets might form, where the building blocks of life are being assembled from the debris of previous stellar generations. Not all irregular galaxies experience starbursts. Some are simply too small or too gas-poor to undergo such dramatic episodes, but all of them share a kind of vibrancy, a sense that they're still evolving, still changing, not yet set in their final form. As we leave this starburst galaxy and continue our journey, we carry with us an appreciation for the diversity of galactic life. Every galaxy is unique, shaped by its own particular history of collisions and mergers, gas accretion, and star formation. Some are old and quiet, others are young and wild, some are massive giants, others are tiny dwarfs barely worthy of the name galaxy. And all of them together, 200 billion strong, make up the cosmic population we've committed to visiting. We're making progress, galaxy by galaxy, slowly building in our minds a complete picture of the universe's galactic ecology. But there are still many forms we haven't encountered. Let's continue and see what else awaits us in this vast cosmic menagerie. There's a type of galaxy that doesn't fit neatly into either the spiral or elliptical category, and astronomers call them lenticular galaxies, from the Latin word for lens. They're shaped like lenses, with a central bulge and a disk of stars, but unlike spiral galaxies, they have no obvious spiral arms and little ongoing star formation. Lenticular galaxies are transitional objects. Many of them are thought to be spiral galaxies that have run out of gas, either through the natural conversion of gas into stars over billions of years, or through environmental effects like ram pressure stripping, where a galaxy moving through the hot gas in a galaxy cluster has its own gas blown away like leaves from a tree in a strong wind. As we approach a lenticular galaxy, The Sombrero Galaxy, perhaps, one of the most famous examples, we see the distinctive lens-like shape edge-on. There's a bright central bulge, yellowish with the light of old stars, and a flat disk extending outward, also dominated by older stellar populations. Around the whole structure, a faint halo of stars and globular clusters extends into space. What's immediately noticeable is how smooth everything looks. There are no bright knots of star formation, no dark lanes of dust, no spiral density waves organising the distribution of stars. The disk is uniform, almost featureless, populated by stars that formed billions of years ago and are simply continuing their orbits around the galactic centre. In some ways, lenticular galaxies are sad. They have the structure of a spiral galaxy, but lack the youthful energy of ongoing star formation. They're like spiral galaxies that have grown old, exhausted their fuel, settled into quiet middle age. But in other ways, they're peaceful, having reached a stable equilibrium that they might maintain for many billions of years to come. As we explore the Sombrero Galaxy more closely, we find that it does contain some dust, visible as a dark lane cutting across the galactic disk. This dust is the remnant of the gas that once filled the galaxy, the leftovers from past episodes of star formation. There's not enough of it to form significant numbers of new stars, but it's there, a memory of more active times. At the centre of the galaxy, like nearly all large galaxies, there's a supermassive black hole. This one is particularly massive, about 1 billion times the mass of the Sun. It's quiet now, not actively feeding, but its gravitational influence extends throughout the inner regions of the galaxy. Stars near the centre move faster than they would if only the visible mass of the galaxy was present, betraying the black hole's hidden presence. The Sombrero Galaxy also has an unusually large population of globular clusters, nearly 2,000 of them, far more than the Milky Way. These clusters orbit the galaxy in a vast halo, each one a compact sphere of hundreds of thousands of ancient stars. They're among the oldest structures in the galaxy, having formed when the galaxy itself was young. And they've survived billions of years essentially unchanged. As we drift away from the Sombrero Galaxy and toward our next destination, we reflect on what lenticular galaxies represent in the larger scheme of galactic evolution. They're a reminder that galaxies aren't static. They change over time, evolving from one form to another through both internal processes and environmental influences. A spiral can become a lenticular. A lenticular can, through mergers, become an elliptical. The categories we use are useful, but they're also somewhat arbitrary, snapshots of a continuous evolutionary process. Every galaxy is in motion, not just through space, but through the phases of its life cycle. Some are young and vibrant, some are old and fading, and some, like the lenticulars, are somewhere in between, having left their youth behind but not yet reached their final form. Understanding this helps us appreciate each galaxy we encounter, not as a fixed object, but as a moment in a long story, a single frame in a cosmic film that's been running for billions of years and will continue for billions more. We've been flying through galaxies for what feels like an eternity now, seeing their stars and gas and dust, their spiral arms and elliptical halos, their bright cores and faint outer regions. But the truth is, we've only been seeing a small fraction of what's actually there. Most of the mass in every galaxy we visited is invisible, made of something called dark matter that doesn't emit, absorb, or reflect light. Dark matter's existence was first seriously proposed in the 1930s, when astronomer Fritz Zwicky measured the velocities of galaxies in the Coma cluster and realised they were moving too fast. The visible mass of the cluster wasn't enough to hold it together gravitationally. Either Zwicky's measurements were wrong, which seemed unlikely, or there was additional mass present that couldn't be seen. For decades, dark matter remained a hypothesis, one way to explain certain observations, but not the only way. Then, in the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies and found something strange. Stars far from the galactic centre were orbiting just as fast as stars closer in, when they should have been moving slower if most of the galaxy's mass was concentrated in the visible disk. The only explanation that fit the data was the presence of a massive dark matter halo extending far beyond the visible edge of the galaxy. As we explore galaxies with this knowledge in mind, trying to sense the invisible mass that surrounds and penetrates everything we see, we start to understand that galaxies aren't really the objects we perceive them to be. The stars and gas, all the light-emitting matter we've been marvelling at, is just the tip of the iceberg. It's like foam on top of the ocean. The real mass, the real gravitational foundation of each galaxy, is the dark matter halo that surrounds it. These halos are enormous. They extend far beyond the visible edges of galaxies, sometimes several times farther than the most distant stars. And they're not made of anything we understand. Dark matter isn't just dim, regular matter that we can't see. It's something fundamentally different. Particles that interact only through gravity and possibly the weak nuclear force, but not through electromagnetism, which means they're completely invisible to all forms of light. Computer simulations show that dark matter began clumping together very early in the universe's history, long before normal matter had a chance to form the first stars and galaxies. These dark matter clumps, called halos, created gravitational wells into which normal matter could fall. The first stars formed at the centres of dark matter halos. The first galaxies were built inside dark matter scaffolding. As we fly through a galaxy's dark matter halo, we're surrounded by this invisible substance. If dark matter particles could somehow be made visible, we'd see them all around us, outnumbering normal matter particles by a factor of 5 to 1. The galaxy would appear as a vast, diffuse sphere of dark matter, with the visible galaxy as just a bright core at its centre, and the structure would be complex. Dark matter halos aren't smooth. They're clumpy, filled with substructure, smaller concentrations of dark matter left over from the merger of smaller halos in the galaxy's past. Some of these subhalos might contain their own small collections of stars, visible to us as dwarf satellite galaxies. Others might be completely dark, containing no normal matter at all, invisible even in principle to any telescope. This hidden architecture is what holds the cosmic web together. The filaments and sheets we observed earlier, the large-scale structure of the universe, is fundamentally a dark matter structure. Normal matter simply followed where dark matter led, falling into the gravitational wells and forming galaxies at the densest points. It's humbling to realise that everything we've been seeing on this journey, every beautiful spiral galaxy and majestic elliptical, every quasar and starburst is just a small luminous component embedded in a much larger dark structure. We're like astronomers studying the lights of cities on Earth from space and mistaking them for the full extent of human civilization, not seeing the dark farmland and forests and oceans that make up most of the planet's surface. The universe is mostly invisible. Most of its mass, most of its gravitational pull, most of its structural foundation is made of something we can't see and don't understand. And as we continue our journey through 200 billion galaxies, this invisible foundation is there with us, surrounding every galaxy we visit, shaping the cosmic web we're navigating, holding everything together with its silent gravitational embrace. Perhaps the most spectacular events we witness on our journey are galactic collisions. We've mentioned them in passing, but now let's slow down and truly observe what happens when two galaxies meet. The antennae galaxies, located about 70 million light-years from Earth, are one of the most famous examples of a merger in progress. Two spiral galaxies, roughly similar in size, are in the process of combining into a single system. The collision began perhaps a few 100 million years ago, and it won't be complete for another few 100 million years. We're catching the mid-dance. As we approach, the first thing we notice are the tidal tails, long streams of stars and gas extending from both galaxies like the antennae of an insect, hence the name. These tails formed as gravitational forces stretched both galaxies, pulling stars out of their disks and flinging them into intergalactic space. The stars in these tails are no longer part of either galaxy. They're orphans, ejected from their homes, destined to drift through the void for billions of years. Between the two galactic cores where the galaxies overlap, we see intense bursts of star formation. The collision has compressed gas clouds to densities where they spontaneously collapse and form stars. Thousands of massive star clusters are being born here, each containing hundreds of thousands of young stars. Some of these clusters will survive to become globular clusters in the final merged galaxy. Others will disperse over time, their stars spreading throughout the new system. Watching the two galactic nuclei spiral toward each other is like watching a cosmic slow-motion catastrophe. They're orbiting their common centre of mass, gradually losing orbital energy to friction with gas and to gravitational interactions with stars. Each orbit brings them closer together. Eventually, probably in another few 100 million years, they'll merge completely, their two supermassive black holes settling toward the centre of the new combined galaxy. When those black holes finally meet, the event will be cataclysmic on a cosmic scale. The merger will release enormous amounts of energy in the form of gravitational waves, ripples in space-time itself. If humanity is still around billions of years from now when the Milky Way and Andromeda merge, we might detect the gravitational waves from our own galactic collision. But for now, we're observing the antennae, and what's striking is how beautiful it is. Yes, it's violent on galactic scales. Two entire galaxies are being torn apart and reassembled into something new. But from our perspective, drifting through the collision at our own pace, it's a spectacular ballet, a dance of gravity and light that's been choreographed by the fundamental forces of the universe. As we explore other colliding galaxies throughout our journey, we notice patterns. Major mergers, collisions between galaxies of similar size, tend to destroy spiral structure and produce elliptical galaxies. The random orbits of stars after a merger create the three-dimensional distribution characteristic of ellipticals. Minor mergers, where a small galaxy is absorbed by a larger one, tend to leave the larger galaxy mostly intact, though they might trigger bursts of star formation or warp the disk. We also see galaxies that have had close encounters without merging completely. These interactions can still have dramatic effects, triggering star formation, warping spiral arms, or stripping away gas. The Whirlpool galaxy, with its classic spiral structure, is being shaped by interactions with a smaller companion galaxy that's currently passing behind it, and we see the aftermath of ancient mergers. Most elliptical galaxies are thought to be the products of past collisions, though those collisions happened so long ago that only careful analysis of stellar populations and orbital patterns reveals their history. The universe has been through many more mergers in its past than are happening right now. In the dense early universe, collisions were common. As the universe expands and galaxies spread apart, mergers become rarer. This is the violent side of galaxy evolution, but it's also the creative side. Mergers trigger star formation. They build larger galaxies from smaller ones. They redistribute matter and reshape structure. Without collisions and mergers, the universe would look very different. There would be no giant ellipticals, no galaxy clusters with their massive central galaxies, just a population of small, isolated spirals slowly converting their gas into stars. As we prepare to leave this colliding pair and move on to the next phase of our journey, we take one last look at the chaos and beauty of galactic merger. It's a reminder that even on the larger scales, the universe is dynamic, changing, never static. Galaxies are born, evolve, collide, merge, and eventually fade. They're participants in a cosmic story that's still being written. We've been travelling through galaxies for hours now, days in some subjective sense, seeing trillions upon trillions of stars. And as we fly, a question naturally arises. In all these galaxies, among all these stars, are we alone? The numbers are almost incomprehensible. Each galaxy contains hundreds of billions of stars. Many, perhaps most of those stars have planets. The Kepler Space Telescope, active in the early 21st century, taught us that planets are common. Not rare. Nearly every star we can see likely has at least one planet, and many have several. If we multiply it out, the observable universe contains something like 10 to the 24th power stars. That's a 1 followed by 24 zeros, a number so large it's difficult to grasp. If even a tiny fraction of those stars have planets in the habitable zone, the region where liquid water could exist on a surface, we're talking about billions of potentially habitable worlds. And yet, we've never detected any sign of life beyond Earth. No radio signals, no megastructures visible in distant star systems, no spreading wave of colonization moving through the galaxy. The universe appears, at least from our limited vantage point in the early 21st century, to be silent. As we explore galaxy after galaxy, passing billions of stars, we look for signs. We imagine what an advanced civilization might build, what marks they might leave on their cosmic environment. A Dyson sphere, perhaps, a structure surrounding a star to capture all its energy, or massive infrared emissions from a civilization's waste heat, or modifications to a planet's atmosphere that couldn't be explained by natural processes. We don't see any of these things, or rather we don't see anything we can definitively attribute to intelligence. Every anomaly we encounter has a natural explanation. Every strange signal is either noise or can be traced to natural phenomena like pulsars or magnetars or cosmic mazes. This absence is what Enrico Fermi wondered about in a famous lunchtime conversation in 1950. If the universe is so vast, if there are so many stars and planets, where is everybody? The Fermi paradox has troubled astronomers and philosophers ever since. If life is common, if intelligence arises regularly, if technological civilizations are a natural outcome of biological evolution, then the galaxy should be teeming with them. And yet, we see no evidence of that. Perhaps life is rare. Perhaps the sequence of events that led to life on Earth, from the formation of complex molecules to the emergence of self-replicating systems, to the evolution of multicellular organisms to the development of intelligence, is so improbable that it's happened only once in the observable universe. Or perhaps life is common but intelligence is rare. Maybe most biospheres remain microbial forever, never evolving complex organisms, let alone tool-using species capable of building civilizations. Or perhaps intelligence is common, but technological civilizations are short-lived. Maybe the window between a species developing technology and either destroying itself or settling into a sustainable equilibrium that doesn't involve spreading through space is very brief on cosmic timescales. Or perhaps we're simply not looking in the right way. Maybe advanced civilizations don't use radio signals. Maybe they've moved beyond physical forms entirely, uploading themselves into computers or exploring dimensions we can't perceive. Maybe they're all around us, and we just don't recognize them. As we continue our journey, passing star after star, galaxy after galaxy, we carry this question with us. It becomes a kind of meditation, a wondering about our place in the cosmic order. Are we truly alone, the only conscious minds contemplating the universe? Or are we just the first, or the last, or one of many but too isolated in space and time to ever make contact? There's a kind of ache to the question, an existential loneliness in the possibility that we might be the only ones looking out at these 200 billion galaxies and comprehending what they are. But there's also a kind of wonder. If we are alone, if consciousness is that rare, then we become precious beyond measure, the universe's way of knowing itself, perhaps the only way. These are questions without answers, at least not yet, but they're worth carrying as we continue deeper into the cosmic expanse. Let's pause for a moment in our headlong journey through galaxies and consider something simpler but no less beautiful, the colours of stars and how those colours change the appearance of galaxies across cosmic time. When we look at a young galaxy, one that's actively forming stars, we see brilliant blues and whites. These are the colours of massive hot stars, stars that burn hydrogen at prodigious rates, living fast and bright for just a few million years before exploding. Their surface temperatures can exceed 30,000 degrees, and at those temperatures stars emit most of their light in the blue and ultraviolet parts of the spectrum. These hot blue stars are what give young spiral galaxies their characteristic appearance, especially in the spiral arms where star formation is most active. The arms glow blue and white, outlined by dark lanes of dust where future stars are gestating. It's a youthful palette, the colours of energy and activity. But as we visit older galaxies, ellipticals or lenticulars that have exhausted their star-forming gas, the colours shift. These galaxies glow with yellows and reds, the colours of smaller, cooler stars that burn their fuel slowly and can live for billions or tens of billions of years. The massive blue stars are gone, having lived their brief spectacular lives and died, leaving behind neutron stars or black holes. What remains are the modest red and yellow stars the cosmic majority patiently shining on. This change in colour is one way astronomers measure the age of stellar populations. The bluer a galaxy, the more recent its star formation. The redder it is, the longer it's been since new stars formed. It's like looking at a forest and distinguishing old growth from new by the sizes and types of trees. And then there's another kind of red, the cosmological redshift that stretches the light of distant galaxies toward the red end of the spectrum as the universe expands. The farther away a galaxy is, the more its light is redshifted, the more its colours are shifted toward longer wavelengths. A galaxy that glows brilliant blue in its own rest frame might appear red to us simply because of the vast distance between us and the expansion of space in the interim. This redshift is one of our most important tools for measuring cosmic distance. By measuring how much a galaxy's light has been redshifted, we can determine how far away it is, and therefore how long ago the light we're seeing left the galaxy. It's a cosmic timeline encoded in colour. As we fly through different epochs, seeing galaxies at different stages of their evolution and at different distances, we're surrounded by a symphony of colours. Young starbursts blaze in brilliant blue. Ancient ellipticals glow a steady yellow-red. Distant galaxies, their light stretched by cosmological expansion, appear even redder, sometimes shifted so far that their ultraviolet light arrives at Earth as infrared, invisible to the human eye but detectable to specialized telescopes. And in all this colour there's information. The colour of a star tells us its temperature. The colour of a galaxy tells us its age and star formation history. The redshift of a galaxy tells us its distance and the age of the universe when that light was emitted. Colour isn't just aesthetic, it's fundamental to how we understand the cosmos. There's something almost musical about it, the way different wavelengths of light correspond to different notes on a cosmic scale. Blue is a high note, the sound of youth and energy. Red is a low note, the sound of age and distance. And all the colours in between, the yellows and oranges and greens, each represents a different story, a different combination of temperature and age and motion and expansion. As we move forward through our journey, we'll carry this appreciation for colour with us. Every galaxy we see is not just a collection of stars, but a palette of light, each hue telling us something about what we're seeing, where it is, and what it's been through. It's another layer of understanding, another way that the universe communicates its nature to those willing to look carefully and think deeply about what they see. Gravity is the weakest of the fundamental forces, and yet it's the force that shapes the universe on the larger scales. It's gravity that holds stars together against the outward pressure of their fusion reactions. It's gravity that binds stars into galaxies, galaxies into clusters, clusters into superclusters, and it's gravity that orchestrates the grand cosmic dance we've been witnessing on our journey. Let's consider what gravity means for the galaxies we've visited. Every star in a galaxy is in orbit around the galactic centre, held in place by the combined gravitational pull of all the other stars and of the dark matter halo. In a spiral galaxy like the Milky Way, this creates a disk configuration. with stars moving in roughly circular orbits, all in the same plane, like planets around the Sun but on a vastly larger scale. The Sun, for instance, takes about 230 million years to complete one orbit around the Milky Way's centre. That's called a galactic year. In the entire history of complex life on Earth, from the Cambrian explosion to today, the Sun has completed barely more than 2 full orbits. Civilizations rise and fall, species evolve and go extinct, continents drift and collide, all in a tiny fraction of a single galactic orbit. And yet, this orbital motion is stable, or at least quasi-stable. The Sun has made thousands of orbits since it formed 4.5 billion years ago, and it will make thousands more before it dies. Gravity doesn't tire. It doesn't weaken with time. It just continues, pulling steadily, holding everything together across unimaginable spans of time. In elliptical galaxies, where stars orbit in random orientations rather than in a disk, gravity creates something different but equally stable. Stars whip around the galactic centre on elliptical paths, some plunging close to the centre before swinging back out to the galaxy's edge, others maintaining more circular orbits. The result is a 3-dimensional distribution that's maintained by the same fundamental force. Gravity also governs the larger scale structures we've observed. Galaxy clusters are held together by gravity. The hot gas between galaxies in a cluster, heated to millions of degrees, doesn't escape into intergalactic space because gravity holds it in place. The cluster itself doesn't fly apart despite the high velocities of individual galaxies, because the combined gravitational pull of all the galaxies and dark matter keeps everything bound. And on the very larger scales, gravity is what's slowing the expansion of the universe. The Big Bang sets space expanding, but gravity has been pulling back, working against the expansion, trying to pull everything back together. Whether the universe will expand forever or eventually collapse depends on the balance between the outward momentum from the Big Bang and the inward pull of gravity. Current observations, as of the early 21st century, suggest the universe will expand forever. And in fact, the expansion is accelerating due to something called dark energy that acts like a kind of anti-gravity. But gravity's pull is still there, still working, still shaping the evolution of cosmic structure, even as it loses the long-term battle against cosmic expansion. As we travel from galaxy to galaxy, we're essentially surfing along the gravitational landscape of the universe. The filaments of the cosmic web are valleys in this landscape, regions where gravity has pulled matter together. The voids are hills, regions where there's less mass and therefore less gravitational pull. Galaxies collect in the valleys, and we're following the paths of least resistance as we navigate from one to another. There's something almost comforting about gravity's persistence. Everything else changes. Stars are born and die. Galaxies collide and merge. The universe expands and cools, but gravity remains, unchanging in its fundamental nature, always attractive, always pulling matter together, always shaping the cosmos according to the same simple inverse square law that Newton first formulated in the 1600s and Einstein refined in his general relativity. It's the thread that connects everything, the invisible force that makes structure possible in the universe. Without gravity, there would be no stars, no galaxies, no planets, no us, just a uniform expanding cloud of gas, growing ever more diffuse as the universe ages. Gravity turned that uniform cloud into a cosmos, a universe rich with structure and form and beauty. And as we continue our journey, we navigate by its pull, following the paths it creates through the cosmic web. We've been talking about cosmic events in terms of millions and billions of years, numbers so large they're difficult to truly grasp. But let's slow down for a moment and really contemplate what time means on these scales. 1 million years is an almost incomprehensible span from a human perspective. Modern humans, Homo sapiens, have only existed for about 300,000 years. 1 million years ago, our ancestors were still evolving, still developing the traits that would eventually distinguish us as a species. Civilizations, writing, cities, All of human recorded history spans just the last few thousand years. A tiny fraction of a million, and yet in galactic terms, a million years is almost nothing. It's the blink of an eye. Stars orbit their galaxies in hundreds of millions of years. Galaxies merge over billions of years. The universe has existed for nearly 14 billion years. A million years is just a small fraction of a percent of cosmic history. This difference in timescales is part of what makes astronomy both beautiful and frustrating. Beautiful because it reveals processes we could never witness in a human lifetime. Changes so slow that only by looking at many different objects at different stages can we piece together the full story. Frustrating because we can't see things happen. We can only infer processes from snapshots. Consider star formation. We can see nebulae where stars are being born. We can see young star clusters just a few million years old. We can see middle-aged stars like the Sun and ancient red giants approaching their ends. But we've never watched a single star go through its complete life cycle. No human ever will. Even the shortest-lived massive stars exist for a few million years, far longer than human civilization. Or consider galactic mergers. We can see galaxies at various stages of collision, from initial approach to final coalescence. We can run computer simulations that show how mergers proceed. But we've never seen a single merger actually happen, because they take hundreds of millions of years to complete. What we're seeing as we travel through 200 billion galaxies is a vast collection of snapshots, each galaxy frozen at a particular moment in its evolution. By seeing many galaxies at many different stages, we can reconstruct the overall pattern, the way galaxies evolved from small irregular systems in the early universe to the spirals and ellipticals we see today. It's like being an immortal photographer who can take pictures but can't see motion. You accumulate millions of photographs of people at different ages, from infancy to old age, and from those snapshots you infer the process of human aging. You've never seen anyone age, but you understand the pattern. This is how astronomy works. We see the universe not in motion but in a collection of frozen moments, and from those moments we infer the processes, the changes, the evolution that must be happening on timescales far longer than human lives, or even human civilizations. And there's a kind of patience required in this understanding, a willingness to accept that we'll never see the full story unfold, that we can only glimpse parts of it. The universe is patient, it doesn't hurry. Stars form when the conditions are right and not before. Galaxies merge over the time it takes, not faster. The expansion of the universe proceeds at its own pace, independent of our desire to understand it more quickly. As we journey through galaxy after galaxy, we're travelling through time as well as space. The distant galaxies we see are young, their light having travelled for billions of years to reach us. The nearby galaxies are old, or at least we're seeing them as they were relatively recently in cosmic terms. We're witnessing the universe's history spread out before us like a tapestry, each thread a different galaxy at a different time. And in all this vastness, all this deep time, we find a kind of peace. Our individual lives are brief, our concerns often feel urgent, but against the backdrop of cosmic time, everything becomes relative. The universe has all the time in the world, literally all the time there is. It can afford to be patient, to let processes unfold over billions of years, to build structure gradually, layer by layer, generation by generation. Perhaps that's something we can learn from it. Patience, perspective, an appreciation for processes that unfold slowly, but lead to something magnificent given enough time. As we continue our journey, let's carry that patience with us. As we travel farther and farther from Earth, from the Milky Way, from the local group, something interesting happens to our sense of location. We begin to lose the sense of having a centre, a home point from which everything else is measured. In the beginning of our journey, we knew exactly where we were. We started at the Milky Way. We could always look back and see it, a distinctive spiral that marked our origin point. But now, having visited hundreds or thousands of galaxies, having crossed billions of light years, The Milky Way has faded from view. It's just another small spiral in the distance, indistinguishable from millions of others. And this is more than just a physical disorientation. It's a philosophical shift. Because the truth is, there is no centre to the universe, no special location from which everything should be measured. Every point in space is equivalent to every other point. Every galaxy has an equal claim to being the centre of its own observable universe. This principle, called the cosmological principle, states that the universe is homogeneous and isotropic on large scales. Homogeneous means it's the same everywhere. Isotropic means it looks the same in every direction. No matter where you are, if you look around at the universe on scales of hundreds of millions of light years or more, you see roughly the same thing. Galaxy clusters separated by voids, arranged in a cosmic web with no particular centre or edge. The implications are profound. It means Earth isn't special. The Milky Way isn't special. Even our supercluster, the Lenticular supercluster, isn't special. We're just one location among countless locations, all equally valid, all equally unremarkable in the grand scheme. This is sometimes called the Copernican principle, named after Nicholas Copernicus, who showed that Earth wasn't at the centre of the solar system. Over the centuries, we've pushed Earth farther and farther from any special position. First, we learned we orbit the Sun rather than being the centre of creation. Then we learned the Sun is just one star among hundreds of billions in our galaxy. Then we learned our galaxy is just one among hundreds of billions in the observable universe. And now we understand that even our location within the universe is unremarkable. As we drift through this galaxy or that, no longer sure exactly where we are relative to home, we experience this principle viscerally. We're not at the centre, we're not anywhere special. We're just somewhere in a vast, mostly uniform cosmos, and any other somewhere would look much the same on large scales. And yet, there's something liberating about this. If nowhere is special, then everywhere is equally valid. Every point in space has its own perspective, its own horizon beyond which information can't travel. From the perspective of a galaxy 10 billion light-years away, we're in their distant past, our light just now reaching them, showing them the Milky Way as it was 10 billion years ago. The universe has no privileged reference frame. There's no view from nowhere that shows the complete objective truth. There's only views from somewhere, from specific locations with specific horizons and specific paths visible to them. And all these views are equally real, equally valid. As we continue our journey, having lost any firm sense of where we are relative to where we started, we embrace this homelessness. We're explorers without a fixed origin point, travellers in a cosmos that has no centre and no edge, seeing what can be seen from this particular path through space and time. It's disorienting at first, this loss of absolute position, but gradually it becomes freeing. We're not trying to return home. We're not measuring everything against some fixed starting point. We're just moving through the universe, seeing what there is to see, understanding that every galaxy we visit is someone else's home, that every point in space is the centre of some observer's universe. This is what it means to truly comprehend the cosmological principle. Not just to know it intellectually, but to feel it, to experience the universe's fundamental sameness and our own fundamental non-specialness within it. And strangely, that non-specialness doesn't diminish us. It connects us to everything, makes us part of the whole rather than separate from it. We've been travelling toward a goal, visiting 200 billion galaxies, but let's be honest with ourselves for a moment. We're never going to reach that goal, not really. 200 billion is a number too large to comprehend fully, let alone to experience galaxy by galaxy. If we spent just 1 second looking at each galaxy, it would take 6,300 years to see them all. If we spent a minute with each galaxy, it would take more than 380,000 years. If we spent an hour, the journey would require more than 22 million years. And we've been spending much longer than that with each galaxy we visit, really exploring them, understanding them, seeing what they have to teach us. So perhaps this journey was never really about the destination. Perhaps it was always about the process, the contemplation of what it would mean to see everything, to know everything, to visit every island universe in the cosmic sea. There's a concept in mathematics called infinity that's relevant here. Infinity isn't just a very large number. It's a fundamentally different kind of thing, a quantity that's larger than any specific number can be. If you try to count to infinity, you never get there. You can count for eternity and still have infinitely far to go. 200 billion isn't infinite, technically. It's a finite number, but from a human perspective, it might as well be infinite because it's so far beyond our capacity to experience individually. We can understand it statistically, mathematically. We can grasp it as an abstract concept, but we can't experience it directly, and maybe that's okay. Maybe the point isn't to see every galaxy, but to see enough galaxies that we understand the pattern, the diversity, the underlying principles that govern them all. Once we've seen a few hundred galaxies, we start to recognize types: spirals, ellipticals, irregulars, star-forming and quiescent, isolated and colliding, young and old. Once we've seen a few thousand, we understand the statistical distributions. How common are spirals versus ellipticals? What fraction of galaxies are in clusters versus the field? How does star formation rate correlate with galaxy mass and environment? Once we've seen tens of thousands, we can appreciate the full diversity while also recognizing that there are patterns. The galaxies aren't completely random but follow certain rules determined by physics and by cosmic history. And at some point, seeing more galaxies doesn't add substantially new knowledge. It refines our understanding, fills in edge cases, discovers rare exceptions. But the fundamental picture is complete. We understand what galaxies are, how they form, how they evolve, how they relate to the larger cosmic structure. So perhaps we can stop counting. Perhaps we can abandon the goal of visiting every galaxy and instead simply appreciate that they're there, that we've seen enough to understand the whole even if we haven't experienced every part of it. This is what scientists do all the time. They study representative samples. They look at enough examples to understand the pattern, and then they extrapolate to the whole. You don't need to measure every star to understand stellar evolution. You don't need to visit every planet to understand planet formation. You need to see enough examples that you can infer the principles. And we've seen enough. Thousands of galaxies in our imagination, representing different types and eras and environments. We've seen spiral arms and elliptical halos. We've seen collisions and mergers. We've seen quasars and starbursts. We've seen the cosmic web and the dark matter scaffolding. We've witnessed the progression from the early universe to today. We understand galaxies now, not perfectly, not completely, but enough to appreciate what they are and what they represent. Each one is a universe in miniature, a collection of hundreds of billions of stars, each star potentially circled by planets, each planet a unique world with its own story. And there are 200 billion of them, or 2 trillion if we count the smallest dwarf galaxies. Spread across 93 billion light-years of observable universe. We'll never see them all, but we don't need to. We've seen enough to marvel, enough to understand, enough to feel our perspective shift in fundamental ways. Let's continue, but gently now, not driven by the need to visit every single galaxy, but simply drifting through what remains of our journey, open to wonder wherever we find it. As we contemplate the galaxies around us, each one frozen in a particular moment of its evolution, it's natural to wonder about the future. What will become of these galaxies in the deep time ahead, in the tens or hundreds of billions or trillions of years still to come? The ultimate fate of galaxies depends on the ultimate fate of the universe, which in turn depends on the nature of dark energy and the geometry of space. Based on observations made in the early 21st century, the universe appears to be expanding, and that expansion is accelerating. If this continues, the future is both spectacular and lonely. First, over the next several billion years, galaxy mergers will continue. The Milky Way and Andromeda will collide, forming Milkomeda. Other galaxies in the local group will merge into this system or into the Triangulum galaxy. Gradually, our local group will collapse into a single massive elliptical galaxy containing all the stars that are currently spread across dozens of smaller systems. But beyond the local group, other galaxy groups will undergo similar processes, and those groups will remain separate from ours forever. The acceleration of cosmic expansion means that eventually most of the galaxies we can see today will cross the horizon beyond which we can ever detect them. Space is expanding faster than light can travel across it, carrying distant galaxies away from us at speeds that make any future contact impossible. In perhaps 100 billion years, anyone living in Milkomeda would look up at the night sky and see only stars from their own galaxy. Every other galaxy would have receded beyond the horizon. The universe would appear to be just one galaxy in an otherwise empty void, just as it appeared to astronomers in the early 20th century, before they discovered that spiral nebulae were actually distant galaxies. Meanwhile, within Milkomeda and other isolated galaxy systems, star formation would gradually wind down. Galaxies contain only a finite amount of gas, and as that gas is converted into stars, the reserves are depleted. Some gas is locked up in long-lived stars. Some is ejected into intergalactic space by supernova explosions and stellar winds. Eventually, perhaps a few trillion years from now, the last stars will form, using up the last remaining cold gas. After that, no new stars. The galaxy would age as its stellar population slowly burns out. Small red dwarf stars, which can live for trillions of years, would continue shining long after all the massive stars are gone. The galaxy would fade from bright blue and white to yellow to red to a dim infrared glow. Eventually, even the red dwarfs would die. Some would fade as white dwarfs. Others might collapse into neutron stars if they're massive enough. The galaxy would become populated entirely by stellar remnants, white dwarfs, neutron stars, and black holes. And even those would slowly decay. White dwarfs and neutron stars would cool over quadrillions of years, becoming black dwarfs and black neutron stars, emitting no light at all. And even black holes, stable on any timescale we can currently imagine, would eventually evaporate through a quantum process called Hawking radiation. The largest supermassive black holes might persist for 10 to the 100 power years, a time span so vast that the current age of the universe is an infinitesimal fraction of it. But eventually they too would fade. The universe would become a cold, dark expanse populated by particles so widely separated that they effectively never interact. The temperature would approach absolute zero. Structure on any scale would erode away. Entropy, the measure of disorder, would reach its maximum. This future, sometimes called the heat death of the universe, is bleak from a certain perspective. Everything we can see, all the galaxies and stars and structure, is temporary on cosmic timescales. Given enough time, it all fades away into a uniform, featureless void. But there's another way to look at it. We exist in a special epoch, a time when the universe is old enough to have formed complex structures like galaxies and stars and planets, but young enough that those structures are still vibrant, still forming and evolving. We live in the middle chapters of the cosmic story when things are most interesting. And even though the universe's future is one of increasing darkness and cold, that future is so distant that it's almost meaningless to beings like us. The Sun will die in 5 billion years. The Milky Way will merge with Andromeda in 4 or 5 billion years. Human civilization, if it survives, will need to adapt to those changes long before we need to worry about the heat death of the universe trillions of years hence. As we continue drifting through galaxies, each one a temporary island of light in the expanding darkness, we can appreciate them for what they are, brief but brilliant flourishes of structure and complexity in a universe that tends, in the very long run, towards simplicity and stillness. They're beautiful because they're temporary. They matter because they won't last forever. This is true of everything, not just galaxies, but stars and planets and people too. Nothing persists forever. Everything changes, evolves, eventually fades, and perhaps that's what makes existence precious, this brief window of time when complexity is possible, when consciousness can arise and contemplate the cosmos that gave it birth. We've travelled so far now, seen so much, that it's worth asking a question that's haunted us from the beginning. What does all this mean? Is there purpose in the universe, in the existence of 200 billion galaxies, each containing hundreds of billions of stars? Or is it all just physics playing out according to the fundamental laws, matter and energy evolving without intention or direction? The scientific answer is that the universe doesn't have inherent meaning in any human sense. Galaxies don't exist for a purpose. They're not trying to accomplish anything. They form because gravity pulls matter together. Stars form because gas clouds collapse under their own weight. Planets form from the leftover disk around young stars. It's all just natural processes, beautiful and complex but ultimately mechanical. And yet, here we are, conscious beings capable of asking about meaning, capable of travelling in our minds through every galaxy in the universe and wondering what it all signifies. We bring something to the universe that wasn't there before, or at least wasn't there in the early universe, the capacity to reflect, to appreciate, to find beauty and meaning in patterns and structures. When we look at a spiral galaxy and feel awe at its perfect symmetry, at the graceful curve of its arms, we're not discovering meaning that was hidden in the galaxy waiting to be found. We're creating meaning, bringing to the cold physics of gravity and motion and radiation a layer of aesthetic and philosophical significance that exists only because we exist to perceive it. This doesn't make the meaning less real. If anything, it makes it more remarkable. We're the universe's way of knowing itself, thinking about itself, finding beauty in itself. Every time a human looks up at the night sky and wonders about the stars, that's the universe contemplating its own nature. Every time an astronomer discovers a new galaxy, or a physicist works out a new equation describing cosmic evolution, that's the universe understanding itself a little better. And perhaps that's the closest thing to purpose we can find in all this vastness. Not that the universe was created with us in mind, but that we've emerged from the universe with the capacity to understand it, and that understanding seems to be one of the most complex and remarkable things the universe has produced. Galaxies existed for billions of years before humans evolved. They'll exist for billions of years after humanity's gone, if we don't survive or if we evolve into something we wouldn't recognize today. The cosmos doesn't need observers. It was doing just fine before consciousness arose anywhere. But while we're here, while we have this brief moment of self-awareness and cosmic curiosity, we can look out at those 200 billion galaxies and find in them something profound. We can use them as mirrors to examine our own place in the cosmic order. We can use them as tools to understand the fundamental laws that govern existence. We can use them as sources of wonder and inspiration, reminding us that we're part of something vastly larger than ourselves. Some people find this perspective comforting. We're not alone in the universe. We're part of the universe, made of the same matter that makes galaxies and stars, governed by the same physical laws, participating in the same grand cosmic evolution. Our atoms were forged in stellar cores and scattered through space by supernova explosions. We're literally made of star stuff, carrying within our bodies the legacy of cosmic history. Others find it unsettling. We're so small, so temporary, so insignificant in the face of hundreds of billions of galaxies, each containing hundreds of billions of stars. What does any human life matter against that scale? What does any human achievement matter when the universe will eventually fade into cold darkness, regardless of what we do? But perhaps both perspectives are true simultaneously. We are small, but we're also the most complex structures we know of in the universe. We are temporary, but so is everything else. We are insignificant in terms of physical size and duration, but we're significant in terms of complexity and consciousness, and the capacity to appreciate what we're part of. As we drift through this galaxy and the next, contemplating these questions without easy answers, we realize that the journey through 200 billion galaxies has become a journey inward as much as outward. We're not just exploring space, we're exploring what it means to be a conscious observer of space, what it means to be a part of the cosmos that can step back and contemplate the whole, and perhaps that's enough. We don't need the universe to have been created for us to find meaning in it. We can create our own meaning, bring our own significance to bear on physical processes that would continue without us, but that gain something, beauty, purpose, understanding, through our observation and contemplation. As we near what might be called the end of our journey, though we haven't visited every galaxy by any means, we find ourselves sitting with questions that have no clear answers. And perhaps that's appropriate. Perhaps it's exactly where we should be. What lies beyond the observable universe, beyond the cosmic horizon beyond which light has not had time to reach us? We can't know. By definition, we can't observe it. But presumably, more galaxies, more cosmic web, extending infinitely, or at least extending far beyond what we can ever see. What is dark matter made of? We don't know. We've inferred its existence from gravitational effects, but we haven't directly detected the particles that compose it. It could be one of several hypothetical particles that physics predicts might exist, or it could be something we haven't even imagined yet. What is dark energy, the force accelerating the expansion of the universe? We have even less idea. It might be a property of space itself, a cosmological constant that Einstein once proposed and then retracted. Or it might be something more dynamic, something that changes over time. We can measure its effects but not yet explain its nature. Why is there something rather than nothing? Why does the universe exist at all? This is perhaps the deepest question, and it's one that science may never answer because it sits at the boundary between physics and philosophy, between questions about how things are and questions about why they are. Are we alone in the universe? We still don't know. We've found no evidence of life beyond Earth, but we've also barely begun to search. The universe is vast, and we've examined only a tiny fraction of it. Life might be common or rare. Intelligence might be inevitable or vanishingly unlikely. We're too early in our search to draw conclusions, and there are countless smaller questions, mysteries within mysteries. How did supermassive black holes grow so large so quickly in the early universe? What triggers quasars to turn on and off? How do the exact properties of dark matter affect the formation of galaxy structure? What's the distribution of planetary systems across different types of galaxies? Some of these questions we'll probably answer eventually, as telescopes get better and theories more refined. Others might remain mysteries for centuries or forever. And new questions will arise to replace the ones we solve, because that's how knowledge works. Each answer opens up new territory to explore, new puzzles to solve. But here's the beautiful thing. We don't need all the answers to appreciate the questions. There's a kind of joy in not knowing, in being curious, in standing at the edge of understanding and looking out at the vast realm of mystery beyond. Children experience this naturally. They ask why over and over, each answer prompting a new question, diving deeper and deeper until they reach questions the adults can't answer. And that's not frustrating to children. That's exciting. That's where the wonder lives. Somewhere along the way to adulthood, many people lose that capacity for wonder. They start to need answers. Uncertainty becomes uncomfortable. Not knowing becomes a problem to solve rather than a state to appreciate. But science, at its best, maintains that childlike wonder. Scientists are people who've kept their capacity to ask quote, _to_, and to be delighted by the mysteries they discover. They're not frustrated by what they don't know. They're energized by it. Every question is an opportunity. Every mystery is an invitation to explore. As we float here among the galaxies, having seen so many and understood so much and yet still confronting vast realms of uncertainty, we can choose how to relate to that uncertainty. We can see it as a failing, an incompleteness, a source of anxiety. Or we can see it as an invitation, a promise that there's always more to discover, that the universe will never cease to surprise us. And maybe that's one of the gifts this journey through galaxies can give us. A renewed sense of wonder. A comfort with not knowing. An appreciation for mystery as something valuable in itself, not just as a problem to be solved, but as a fundamental feature of existence worth preserving. The universe is under no obligation to make sense to us. The fact that it makes as much sense as it does, that we can understand as much as we have, is already remarkable. And the fact that there's still more we don't understand, that might be even more remarkable, because it means the journey of discovery can continue as long as we're willing to pursue it. Let's begin the journey home now, or at least toward what we remember as home, though we've travelled so far that home might feel different when we arrive. We retrace our path through the cosmic web, though not exactly the same path. We visit different galaxies on the way back, seeing new variations on familiar themes, another spiral here, another elliptical there, another merger in progress, another quasar blazing in the distance, each one unique, each one similar to others we've seen, the universe endlessly creative within certain fundamental constraints. As we approach the local group again, we start to recognise landmarks. The Andromeda Galaxy comes into view, that great spiral that will one day merge with the Milky Way. The Triangulum Galaxy, with its perfect pinwheel structure, the Magellanic Clouds, satellite galaxies that orbit the Milky Way like small moons, and then, finally, the Milky Way itself, our home galaxy. After visiting so many others, seeing it again is both familiar and strange. Familiar because we know its structure, its size, its population of stars. Strange because we're seeing it from outside, a perspective we've never really had before except in artistic reconstructions. We can see the spiral arms winding outward from the bright core. We can see the dust lanes cutting across the disk. We can see the halo of globular clusters surrounding the main structure. And somewhere in all that light, lost among hundreds of billions of stars, is the sun. And around the sun, 8 planets, one of them bearing life, bearing consciousness, bearing the only beings we know of who can make this journey in imagination. As we descend back into the galaxy, passing through the outer halo and into the disk, stars become individual points of light again rather than the merged glow of distant galaxies. We recognise some of them. Betelgeuse, a red supergiant nearing the end of its life. Sirius, the brightest star in Earth's sky. Alpha Centauri, the nearest stellar system to the Sun. And then, there it is, our Sun, a yellow dwarf star, medium-sized, middle-aged, unremarkable in almost every way except one. It's ours. It's the star that gave rise to the planets we know, the star whose energy powers life on Earth, the star that features in every sunset and sunrise humans have ever seen. Around it, the planets, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter and Saturn with their magnificent rings and many moons, Uranus and Neptune in the outer system, and beyond them, in the cold darkness, countless small objects in the Kuiper belt and Oort cloud, remnants of the solar system's formation, and Earth. Blue and white and brown and green, the only planet we know that bears life. From space, it's beautiful, fragile-looking, a delicate sphere of water and rock and atmosphere hanging in the void. All of human history happened here. Every war and peace, every birth and death, every triumph and tragedy, all on this one small world orbiting this one average star in this one typical galaxy among 200 billion others. Coming home after travelling through so many galaxies, Earth looks different, smaller. Perhaps more precious, more worth protecting, because we've seen the vastness of the universe, and we know how rare and special this place is. Not because Earth is at the centre of anything, not because we're cosmically significant in terms of size or age or duration, but because we're here, now, conscious and capable of understanding our place in the cosmos. As our impossible vessel settles onto the surface, as we step out and feel gravity pulling us down, as we breathe air that's the right temperature and pressure and composition to keep us alive, we realise something. We've travelled through 200 billion galaxies, or at least through enough galaxies to represent them all. We've seen quasars and mergers, spiral arms and elliptical halos, cosmic web and dark matter scaffolding. We've witnessed the universe from the earliest galaxies to the most recent, from the smallest dwarfs to the largest giants, and now we're back where we started. But we're different. We've changed in ways that are hard to articulate but profound nonetheless. We see the night sky differently now. We know what those points of light represent. We understand the vastness they're embedded in. We appreciate both our cosmic insignificance and our cognitive significance, our smallness and our capacity for wonder. The journey has ended, but in another sense it continues, because we can never unsee what we've seen, never unknow what we've learned. Every time we look up at the stars, we'll remember the galaxies beyond them. Every time we contemplate our place in the universe, we'll carry with us the perspective gained from our impossible journey. And that perhaps is the real destination. Not any specific galaxy, not even returning to Earth, but the transformation that happens inside us when we truly try to comprehend the cosmos we're part of. We're home now, but home is different. Or we are, and the night sky will never look quite the same again. We've travelled together for a long time now, you and I. More than 2.5 hours of imagining what it would be like to fly through every galaxy in the universe. We didn't make it through all 200 billion, not even close. But I think we've seen enough to understand what they are, what they represent, what they teach us about the cosmos and about ourselves. From our starting point at the Milky Way, we journeyed to Andromeda and Triangulum, explored the local group's smaller satellites, ventured into the Virgo cluster, witnessed the cosmic web taking shape. We saw quasars blazing in the early universe, spiral galaxies in their prime, elliptical giants in their quiet maturity. We passed through merger zones and starbursts, visited irregular galaxies and lenticular intermediates. We contemplated the dark matter that binds it all together and the dark energy that will eventually tear it all apart. Along the way, we asked questions about life and meaning, about time and scale, about our place in this vast cosmic ocean. We found some answers, or at least partial answers, and we discovered many more questions worth asking. And perhaps that's the most honest answer I can give you. The universe is vast and mysterious and beautiful, and we've only just begun to understand it. If you enjoyed this slow drift through the cosmos, I hope you'll return for more explorations. The universe is endlessly fascinating, and there are always new questions to ask, new perspectives to consider, new wonders to appreciate. And to those of you who've been on these journeys before, thank you for coming back. Your presence makes these explorations feel less like solitary wandering and more like a shared meditation on the nature of existence. Wherever you are in the world tonight, I hope you're comfortable. I hope your breathing has slowed, your thoughts have quieted, your body feels heavy and warm against whatever surface is supporting you. I hope the day's concerns have receded, at least for now, and that you've found some peace in contemplating distances so vast they transcend everyday worries. Look up at the night sky, if you can, or imagine it if you can't. All those stars, each one a sun like ours, many of them circled by planets we'll never see, and beyond the stars, the galaxies, 200 billion of them stretching across 93 billion light-years of observable universe, each one a cosmos unto itself, each one filled with hundreds of billions of stars, each one evolving and changing and participating in the grand cosmic dance that's been unfolding for nearly 14 billion years. And here we are, conscious beings on a small planet orbiting an average star in a typical galaxy, capable of imagining all of this, capable of understanding our place in it. We're both insignificant and remarkable, both tiny and profound, both temporary and connected to everything that's ever been or ever will be. We're made of atoms forged in stellar cores, organised by 4 billion years of evolution into something that can look back at the stars and understand where those atoms came from. There's a kind of peace in that understanding, a feeling of being part of something larger than ourselves, of being connected to the whole cosmic story rather than separate from it. We're not alone in the universe, not because there might be other intelligent beings out there, though there might be, but because we are the universe, one small part of it looking back at the rest and finding it beautiful. Sleep well tonight, and dream of galaxies if you dream at all. Dream of spiral arms and elliptical halos, of stars being born in nebulae and dying in supernovae, of cosmic distances so vast that light itself takes billions of years to cross them. Dream of the universe as it is, vast and ancient and beautiful, and of the remarkable fact that we exist within it, able to contemplate and appreciate and find meaning in what we see. Good night.